So without any further ado, let's get started. And it is a great privilege for me to invite our first invited talk speaker, Dr. Amit Dhurandhar. Just to give you a quick overview about Amit's background. Amit Dhurandhar, he's a research staff member in the Trusted AI department at IBM TJ Watson Research Center, where he leads the research on explainable AI. His current research focus is basically around enhancing trust in systems that try to explain and understand their behaviors. Most of his recent research in this area have been published at extremely prestigious venues like NeurIPS, ICML, and GMLR. And understandably, a lot of his work has also been picked up by the popular press like Forbes magazine and PC magazine and things like that. A lot of his work is available to the data science community through the open source AI Explainability 360 toolkit. And what is actually very interesting about Amit is, so a lot of us spend our life of research becoming experts in one area. Amit has managed not just to do that in one, but even multiple areas. For example, before explainability, he has done extremely interesting work in the area of olfaction research, where his work has been published in reputed journals like Science and Nature. So it's just amazing. And just on a personal front, Amit and I go way back to our school days, and he has been an excellent friend and mentor to me right from our BTech project days, and I'm sure to many other researchers in the machine learning community. So it's a great privilege for me to invite Amit here to speak to us at CORD's invited talk. So with that, let's get started with the talk. Over to you, Dhwani, to present the talk. And feel free to post your questions in the Q&A option on Zoom. We will have Amit respond to all the questions at the end of the talk. Thank you.
Hi, Happy New Year, everyone. So my name is Amit Dhurandhar. I'm a research scientist at IBM TJ Watson, New York. And today what I'll do is I'll talk about my perspective on explainable AI. So as we all know, explainable AI is used in almost all industries now, ranging from credit risk to employment, to admissions, to prison sentencing, and so on and so forth. So given this inculcation into society of ML as well as deep learning models, it's no longer that it's sufficient for a system to be just accurate on your test data that you test in the lab, for instance. So there are all these questions of, is the model fair? Is it easy to understand? Is it easy to tamper with? Is it accountable? And so on and so forth. What I'll do in this talk, though, is focus on the second part about understandability and show how it also relates to many of these other aspects. So besides entering many parts of social life, explainable AI has also gotten a lot of traction in media over the last few years, and for good reason. So the sudden expansion has been because of the proliferation of deep learning. Given that these deep nets are highly opaque, using them in critical applications begs the question of what are they actually doing, or what is it that they're truly focusing on, and can we trust these models? Also, laws such as the General Data Protection Regulation, which is passed in Europe, asks for meaningful information from any automated system that makes decisions for humans. So besides trust, are there other applications of explainability? And as it turns out, there are. So for example, model simplification is one. So a few years back, there was this case where a huge neural network was trained to distinguish malware from regular code. And someone distilled the network, and it turned out that most of its performance could be attributed to a single rule of if the code had comments or not. So presumably someone building malware wouldn't be careful enough to comment their code, which is obvious, right? A second example is in model debugging. For instance, there was this case where a braking system that was designed and which was trained was deployed in a certain car, and it was seen that the car sort of slowed down when it saw the red light, but it did not stop completely. And the reason was that the place where the model was trained, what happened was in that system, when the red light was seen, a car slowed down and something called as a lurch kicked in. And once this lurch kicked in, the model had trained that then only you stop the car. However, when it was deployed in a different car, the lurch never kicked in, so the car just kept moving, although slowly. Finding confounders can also be another sort of application where in a healthcare data set, it was seen that a model built was picking pneumonia as one of the critical factors for predicting diabetes. And experts know that there is a little relation between the two. But the reason this happened is because a lot of people, or probably all of them, who get pneumonia are admitted to the hospital. And once they're admitted to the hospital, different checks are done, right, for vitals, such as sugar levels, blood pressure, and so on and so forth. And so most of these people do not have diabetes. And so if you have a data set which has pneumonia as a feature and you're trying to predict diabetes, it can show up. But identification of such things using explainability is possible. Another sort of use is that in many critical applications, it's rarely that the system makes the final decision. It's usually a human in the loop. And so for the human to understand why a system is making such a certain recommendation is important. So even though you might have a more accurate black box model, it's beneficial to maybe have a slightly less accurate but interpretable or some form of explanations where a human can understand reason and then make a decision. Because this combination of a human with with an interpretable model might actually lead to a better on-field performance. With things such as fairness and robustness and generalizability, explanations are becoming more important. For example, there's this very commonly known example of classifying wolves and dogs, and this network was trained, which was very accurate. And once someone tried to actually interpret it, it turned out that since most pictures of wolves are taken in snow and most pictures of dogs are taken on grass, the neural network was basically just detecting snow as a feature or as an indicator of wolves, rather than actually focusing on the features or the facets of the wolf. So things like this can be uncovered, which are very important if you want widespread adoption and deployment. So now, in this part of the talk, I will sort of very briefly go over different types of explainability and different types of a few different types of explainability methods. So explainable AI methods can be broadly segmented into either being directly interpretable or post hoc, or global or local, or static or interactive. Examples of directly interpretable methods are things like decision trees or rule lists, where it's clear to the user of how a particular decision or a set of decisions were made. However, when you have a neural network or a deep network, it's unclear of how the decision was made, and so you need post hoc methods. Another example model is when you use ensembles, for example. It's not clear where you use different kinds of models of how exactly a decision was arrived at. So in such cases, you can have local interpretation where you're just trying to explain a particular point or a decision behind a particular point. And one very popular method is LIME, which stands for Locally Interpretable Model Agnostic Explanations, which essentially fits sparse linear models around the point of interest. And interpreting this sparse linear model, which is a proxy model, is considered to be an explanation for why the original model made its particular decision. There are also other methods, local methods, such as saliency maps for images, which essentially try to see what is the change in output with respect to the input. And for example, the top row is a set of input images, and the bottom row is a set of potential explanations it comes up with, which is essentially a heat map of regions that are highlighted and which it surmises is what the model is looking at when classifying these different sets of objects. For global interpretation, usually a simple, directly interpretable model is trained. And there are methods, these are called knowledge transfer methods, and there are methods such as knowledge distillation or profit and S ratio, which transfer information from a complex black box model to a simple model and creating a much more faithful simple model than just direct training. And these essentially are useful in applications where you want global interpretability or just some other sort of resource constrained deployments and so on. So as we have seen, there are different types of methods and there are different methods, and also there are different kinds of explanations. So you can have local, global, feature-based, example-based, and so on and so forth, depending on the application. But in all of these, there are generally two major things that a good explainability method is trying to accomplish. The first thing is essentially the stage one here, where it's trying to as accurately as possible mimic the complex model, either locally or globally, or even at a group level. And in the second stage, it's trying to make it as accessible to the human as possible. So essentially, an explainability method can be split into these two broad stages. And this is something I have discussed in a recent blog of mine, which came out on KD Nuggets a couple of months back, whose link is at the bottom, and you guys are welcome to look at if you're interested. But the use of this sort of breakup into stage one and stage two is that besides conceptual understanding, it can also lead to some interesting methods, as we'll soon see. The stage one also, as it turns out, is much easier to formalize, because what you want is just fidelity of a proxy model or a simple sort of hypothesis class with respect to your complex model. However, the second part is much harder to formalize because it's about mapping to the human mental model. And that's why we have seen that, especially in the last 1 or 2 years, there's been a surge of research papers which do user studies, because they're trying to sort of justify their model with respect to stage two. So some of the methods that I discussed before, like LIME or even small rule learning and so on and so forth, try to have this intermingled view where they're trying to accomplish both at the same time, where they're trying to fit a faithful model, but at the same time make it as consumable as possible for a human by being sparse generally. However, as I was saying, there's no need for doing both of these things at the same time. So for example, a typical approach, which is one hop, is what is shown in the first row of this slide. However, we could potentially envision an approach where, rather than going directly from the black box model to the proxy model, which is consumable, we could have intermediate models that do not have to be consumable. But when we fit our consumable model to these intermediate models, you might get a much more faithful kind of consumable proxy model. And this is something that has not been explored, at least as far as I know. And it could be something very interesting to look at. And we have already started looking at some of these things, and I'll sort of give you I'll give you a taster essentially of the preliminary results that we have. And one of the things is that this is not just useful for explainability, but like in the first highlighted case here, but is also useful for learning in small data settings as well as resource constraint settings. Because you can have, for example, in the resource constraint setting, you can only have a small model that can be maybe deployed on an edge device or in UAVs, or have other kinds of constraints, and this kind of transfer mechanism could be useful. Also in small data settings where you might have a small data set where you can only train a simple model, but then you have a complex model on some larger corpora, and you could potentially use some of these transfer schemes for improving a simple model. So here is a toy example which I tried to see if the approach that I was mentioning has any merit. So what I did here was I initially created a black box model, which is nothing but a 5th degree polynomial. and I added some little bit of noise for the first 20% of the data. So the red curve you see is that. Then what I did was I fitted just a simple linear regression, but with bi-square loss, which is a convex loss, but which is a robust kind of convex loss, to this red line, and which is basically the yellow line. And so you get some fit, and if you compute the mean squared error of this line, it's around 2.29. Then I tried the the multi-hop approach, and here in particular a two-hop thing where I had my black box model, but then I fit a third degree polynomial to this fifth degree polynomial, and now to this third degree I fit a linear regressor, and which gives me the green line. And as you can see, the mean squared error for this line with respect to the original black box is much smaller. I saw similar sort of qualitative results even if you remove the noise, so which is very interesting. And since losses here are convex, it's not that there's some instability in terms of finding better local minimas, but it's mostly because there's a subtle point here that the evaluation loss is different than what your simple model is optimizing. And that's typically the case, because usually for classification problems, accuracy is reported, which is 0-1 loss. However, most methods, or almost all methods that I know, don't really optimize this, but they optimize some other loss. For example, like logistic regression optimizes log likelihood, or decision trees optimize some kind of Gini gain or information gain, and so on and so forth. So this is a very realistic scenario, and it's interesting that given this loss mismatch of evaluation in relation to what a simple model is trained on, you can actually get improvements with this multi-hop approach. So here is more of a taster where we chose a black box model to be a deep net. The simple model was LeNet, which is a much more shallower network. And on CFAR10, we saw that when we trained the LeNet directly, we had an accuracy of 61.5% after we ran it for tens of epochs. Direct transfer using distillation, it enhanced to 68%. But when we did this transfer, the multi-hop transfer, where MobileNet was one of the intermediate models, we got even further improvement. And qualitatively, we saw something similar even for CFAR100. So these are just initial results, but they show the promise of this approach of knowledge transfer. One thing I would say, independent of the previous point, is that there's also a lot of talk about causality and causal explanations and so on and so forth. However, just uncovering the true causal mechanism of, say, a black box model or something else does not directly lead to an understandable solution, as the causal graph and so on and so forth could be very large, and sometimes even there might be certain latents which may not be even discoverable. So it still essentially corresponds to stage 1 of the process, and stage 2 would still be required to make this consumable. Here's an interesting article by Jeff Hinton, which many of you might have seen, arguing about the need for explainability. So this may be something that you guys might want to look at and ponder about. So one of the criticisms for explainability is that, a neural network has so many neurons and connections. How can you really understand what's happening at that level? However, I would argue that, in the real world, we trust people and we act based on other people's verbal cues as well as actions. And it's not that we understand what's really happening in their brains in terms of which neurons are firing and so on and so forth, but it's mostly in the action space based on their emergent behavior. And so my sort of understanding is, or my claim is, that we don't really need to understand every neuron activation and weights and so on and so forth. All we really need to understand is just one faithful representation of the model. So for example, in the human case, that would be like actions and even verbal cues and so on and so forth. You could see those as a representation or a manifestation of the neural activity in someone's brain. And as long as these actions and other sort of behaviors are faithful to what's really happening to the person, understanding them and trusting them is sufficient. So even for models, we don't really need to understand every neuron or every little weight that's varying, but we just need to understand one representation. It's sufficient to understand one representation that's faithful to what the model is doing. And although one has to find this representation, it's kind of, at least for me, some a sort of comforting aspect that you do not really have to try to understand every possible representation that someone might come up with, but it's just sufficient to look at one. And with this, I would like to end my talk, and I'd be very happy to take questions during the Q&A. Thank you very much. Thanks.
Great. Thank you very much. Thanks, Amit. So we have a lot of questions that have come in. Let me just try to cluster them. And so there have been quite a few. Let me start off with this. So there have been quite a few questions related to the two-stage approach. It has evoked a lot of interest. So the first question from Prabhat is, what is the intuition that the multi-hop will work better? And does it depend on the complexity of the stage one model?
Hi, everyone, and thanks, Karthik, for the really kind introduction. I think it's probably one of the best introductions I've had. So thank you, and thank you all for attending. So very good question. So my intuition was mostly, it came out not from this subtle thing of loss mismatch, which I mentioned, but it mostly came out of this thing of just smoothing the behavior. Because as we've seen, for example, in distillation and so on and so forth, one of the reasons it works is that like a simple model does not really, it's hard for it to fit all the peaks that a complex model might fit, because because it has a very rich hypothesis space. And so what it does is essentially it sort of flattens out the peaks. And some of the work that I've done over the past couple of years in this particular direction is we do a different kind of strategy where we sort of weigh, rather than changing the target, we essentially reweigh the training set. And that helps, again, the simple models. But if you see what the reweighing is doing, in a way, it's also kind of smoothing the landscape. So it seems that it's all about smoothing the landscape. And so the multi-hop approach, since you would presumably use simpler and simpler models as the intermediate models, it would the hope is that this will essentially smoothen it in a way that's more sort of conducive for the simple model to get over its own inductive bias and fit the best possible, say if it's a linear model, the best possible line that will generalize the best. So that's the idea. And since it's multi-hop, if you wanted to do sort of a direct fit, that's just a special case of it. So I mean, so it's not that it's not one or the other, right? Because you would anyway, in whatever algorithm or whatever search procedure you use, that would be one of the candidates, because that's the simplest candidate to anyway search for. But it's interesting kind of that people for local or global explanations where you, or methods which basically in both these cases which use proxy models, you kind of try to directly fit, and it kind of intuitively you would want to do that because people would think, why do you need essentially middlemen, so to speak? But as I've shown, I mean, at least with the initial experimentations on the toy problem, as well as some of the little more realistic ones, there seems to be a lot of promise, and it's not that simple where you just fit something direct and that does well. And like I said in the presentation, I don't know if I focused enough. This thing of the loss that you evaluate on is typically different than what a model trains on. I mean, I gave some examples of logistic regression and decision trees, but even if you take a neural network, you don't really train it on 0-1 loss. You train it on cross entropy. So which is, so there is some mismatch in terms of what you train the models on and what you might finally evaluate them on. And because of this, there is actually, I think, a lot of potential there where, like I mentioned, it's not just for explainability, but also other applications where it might be used.
Cool. The next question is from Samarth. So how do you view the gap between performance of a strong model versus a weak but explainable model? Is it some dataset specific correlations that are helping, or latent undiscovered nodes in a causal graph? Like, should we ignore them as flukes or something?
Yeah, so I think it's so I guess it depends on the situation, but usually the black box models do well because you have a higher representational power. So the data set is very complex. You can essentially think of the model sort of clustering and drawing small circles around as you go higher up in, say, a deep network, for example. Like there's more and more refinement that happens. So if you use just a simple interpretable model, it may not be able to get that refinement, and due to which you may not get that accuracy on at least a distribution that matches what the complex model is trained on. But it's possible that, you know, like there's also a lot of like work done now, and there's a lot of interest on distribution shifts and basically out of distribution generalization. That's like a really hot topic these days. So it's possible that it may be that, you know, the simpler model might actually be more robust, although it has higher error on something that sort of matches very closely the distribution that you have trained the model on. The other thing, like I mentioned, I think in one of the sort of applications is that in many critical applications, it's not like the system will directly make a decision. Usually it will be like a decision support system. So even if the model is suboptimal, but because the human can understand it, the overall system performance will be, in many cases, much higher than just having a black box model directly making decisions, just because of this sort of collaborative effort. So I think in real world settings, there are, I think, motivations for having simpler models. And these transfer mechanisms actually kind of, in some sense, at least from the simple model perspective, give you best of both worlds, because you can always train your simple model on the original data, see how it does, then try these transfer mechanisms, and if they don't give you better results, you just use the original model. So in a sense, there's nothing to lose. I mean, might as well give it a shot and try these things.
Cool. Some questions on the chat as well. We have 2 minutes, so let's try to squeeze in one more question. So this is asking this is asking about the link between causality and explainability. In particular, there's a lot of hype around causality, causal explanations, and so on. So wanted your comments on that.
Yeah, so I think, like I said, just uncovering the causal mechanism may not lead to something that's understandable, because there are a couple of reasons. First, I mean, like the causal mechanism may be so complicated that one may not understand. The second is that there might be certain latents which may not be even interpretable, in terms of we may not be able to understand what they are. Now, if you come to causal explanations, I think there have been actually a couple of interesting works in this year's NeurIPS, that is NeurIPS 2020, with respect to SHAP and stuff, where for certain kinds of causal graphs, they have shown how you could compute Shapley values. So if you had essentially additional information. So I think I think that direction is very promising. And in fact, some of the work that I'm involved in is that I'm pursuing is also in that direction, where I'm trying to get like causal is a very strong word, but at least things that are more robust or invariant to sort of noise and shifts is something that I am also kind of currently working on. And I think it's a very promising direction where a lot of work can be done.
Cool. And we'll do one final question. So this is by Anirban. Can explainability help to suggest an action of recourse? For example, explainability can be used to explain a loan rejection, but can it help to recommend the most cost-effective course of action to get it approved?
Right. So there is actually, again, in the NeurIPS this year, there have been some papers, and so there's a lot of effort being done where rather than just changing arbitrary attributes, like say, for example, age, right? Like if someone tells you, oh, if you were 20 years younger, your loan would have been approved. That's kind of useless, where you focus on, where the methods focus on actionable features, and which allows you to sort of suggest which are the actionable features, and then you can essentially try to manipulate those. In fact, we during NeurIPS, we had like an independent independent discussion, and we have also, I think, a YouTube recording, which probably I can share, where the topic was algorithmic recourse and counterfactual or contrastive explanation. So maybe, yeah, you can have a look at the video, and yeah, if you have any questions, you can always reach out.
Cool. Thank you very much, Amit. We're at the end of the hour. It was great having you. Thanks again for the talk.
Thanks. Thank you.
Have a nice evening.
Bye.